In this video, we're going to talk about lines and planes of best fit. In the previous video, we talked about the least squares problem, and we saw that a least squares solution, so recall that a least squares solution to the equation ax equals b is a vector x star that satisfies the equation A transpose A x star equals A transpose B. That's what a least square solution to Ax equals B is. That is a vector x star that's not necessarily a solution to Ax equals B, but it's a vector such that Ax star is as close to B as it can get. And in this video, we're going to apply that to lines of best fit. So let's take a look at an example. The question is there a line, and the line has equation y equals mx plus b that goes through the points 1, 1, 2, 2, and 3, 4. Well, if you think about it, I think you'll see that the answer is no, right? Because if you look at these 2 points, the slope of a line through those 2 points is 1, whereas if you look at these 2 points, the slope of a line through those 2 points is 2. So there's no line that goes through all 3 points. And we can see that visually by graphing the points. Here's 1, 1, here's 2, 2, and here's 3, 4. But we can look for a so-called line of best fit. So there is no line. Instead, we can find the so-called line of best fit. And what that means is that it's the line such that when you look at, okay, that's supposed to be a straight line. When you look at the error, so let's zoom in a bit. Let's say that you have a point here, which is x1 comma y1. And you have a line y equals mx plus b like this. When you plug in x1 into the equation of the line, you get a point here, which is called y1 hat. So y1 hat is equal to m times x1 plus b. And the difference between y1 and y1 hat is called the error. So y1 minus y1 hat is the error. It's how off you are from the actual y value, right? The actual y value is y1. Now what we want the line to do, the line of best fit, what you do is you take all the errors and it will minimize the sum of the squares of the errors. Okay, so this line minimizes the sum. Let's say that you have n points. I'm writing out the general formula. I equals 1 to n, the sum from I equals 1 to n of yi minus yi hat squared. So n is the number of data points. In this example, there's 3, right? You have x1, y1, x2, y2, and x3, y3. Well, let's think about the connection between x1 and y1 hat. Each m and b will give you a different y1 hat, a different y2 hat, and a different y3 hat. The connection is that yi hat is equal to m times xi hat, m times xi plus b. And so what we're really looking for is we want m and b, the slope and the y-intercept of the line, so that the sum from I equals 1 to n of yi minus yi hat squared is as small as possible. So we're looking for m and b. And let's look at this expression. This expression is the same as, let's see here. This expression is equal to the norm of the vector y1 minus y1 hat, y2 minus y2 hat, all the way to yn minus yn hat. It's that norm squared. It's the length of this vector, or the magnitude of this vector squared. That's one way to think about this expression that we have. And so we can minimize, if we're trying to minimize the square of some positive or some non-negative number. So we can minimize this vector, the magnitude of this vector, y1 minus y1 hat, up to yn minus yn hat. We're trying to find m and b that will make this as small as possible. Now this is the same as the magnitude. I can split up these vectors into y1 to yn, that's a vector we're given, minus y1 hat, y2 hat, all the way to yn hat. Okay. Now, what is the connection between the yi's, okay, this vector, and m and b? Well, this vector, okay, let's call this vector like this. If you write it like this, okay, it's m times, each yi hat is m times xi plus 1 times b. And what that means is if you write things like this, where a matrix where the first column is x1 through xn and the second column is all ones, it's this times mb. It's that vector mb. Do you see why this is true? Because if you multiply this matrix by this vector, you get, so just to clarify what that is, that's the first component is m times x1 plus b. The second component is m times x2 plus b all the way to m times xn plus b. And the yi hats were equal to m times xi plus b. So this vector is in fact the same as that vector. Now let's call this matrix A. So what we're trying to do is we're trying to find the vector MB that makes this vector, which is right there, that makes the vector A times MB, that's this vector y1 hat to yn hat, as close as possible to the vector y1 to yn. Well, where have we seen that before? This is a least squares problem, right? We're trying to find this vector. See, in the previous scenario, this would be like our x star, and then this vector is like our vector b. But let's, for the sake of this problem, let's call this vector y instead of b, because I don't want to mix it with the y-intercept. So what we're seeing is that from the formula, A transpose A times the vector MB equals A transpose times y. And we can solve this for the vector MB, and that will give us our best fit line. So in this example, we had x1 is 1, x2 is 2, and x3 is 3. So our matrix A is 1, 2, 3, and then the second column is 1, 1, 1. Okay. And our vector y was consisting of y1, y2, and y3. That's 1, 2, 4. And so now we just solve for MB. All right, so we need A transpose. A transpose is this matrix. And so therefore A transpose A is this matrix times this matrix. And when you multiply it out, you're going to get this matrix. We also need A transpose Y. A transpose Y is going to be this matrix times the vector 1, 2, 4, and that's going to equal 17, 7. So what we need to do is we need to solve this system. It's this matrix times the vector MB equals that vector. And we know how to do that. We just set up the augmented matrix. Now we could multiply by the inverse. We could multiply both sides by the inverse of this matrix, but I think it's easier to just solve this using elimination. You're going to get some annoying fractions though. We should divide the first row by 14. And then replace row 2 by 6 minus, row 2 by row 2 minus 6 times row 1. And when you do that, you get this. finally we divide, well not finally, the next step is to divide row 2 by 3/7, and that gives us this. And then the last step is to replace row 1 by row 1 minus 3/7 row 2. And that gives you, what do you get when you do that? So 17/14 plus 2/7 is 21/14. That's 3/2. And so there we see that this vector MB is 3/2 negative 2/3. So what's the line of best fit? The line of best fit for those 3 data points is y equals 3/2 x minus 2/3. And if you plug in these data points into a calculator that finds the line of best fit, you will in fact get this line. So that's how to find the line of best fit. Of course, the method we did, this was just a particular example, the method we did applies in general. So we set up this matrix A. We're given the x1 through xn, so we can find this matrix A, and we're given the yi's. And so by what we talked about when it comes to least square solutions, we just need to solve for this vector MB. And we see the connection between the line of best fit and the least squares. The point was that we wanted to minimize this sum of the squared errors and we saw that that ends up amounting to minimize the length of this vector, which is the same as finding MB that makes A times the vector MB as close as possible to Y, and that's a least squares problem that we were able to solve. Okay, so that was the line of best fit. I also want to do an example of the plane of best fit. We're done with this example. Let's go on to the next example, the plane of best fit. And it's the same general concept, except now we have data points with 3 coordinates. So let's say that you have these data points, 1, 0, 0, 1, 1, 1, 2, 3, negative 2, and 4, 0, negative 1. And the question is, what's the plane of best fit through these points? And you can check by setting up a system of equations that there's no plane that goes through all 4 points. But we want the plane of best fit. So here we're given these xi's, the yi's, and the zi's. And what are we trying to do? We're trying to find a plane. So a plane is going to have the form z equals c1x plus c2y plus c3. We're trying to find a plane such that if you set zi hat equal to this, you want to minimize again, the sum of the squares of the errors. Sum of squares of errors. And what is that? The sum of the squares of the errors. In general, if you have n data points, it's the sum from I equals 1 to n of zi minus zi hat squared. And again, this is the same as the square of z1 zn minus z1 hat zn hat squared. And now we see what we should do. We should call, let's see. This time I will use the letter b for this, the vector b. And then this part is a times the vector c1, c2, c3, where a is, these are xi, yi's. Where a is the matrix where you have x1 through xn, y1 through yn, and then all ones. Right? Because if you take this matrix and multiply it by this vector, you're going to get the first component is c1 x1 c1 x1 plus c2 y1 plus c3 c2 x1. Let's see, I'm getting mixed up. Okay, let's just multiply this out. So if you take a times c1, c2, c3, you're going to get c1 x1 plus c2 y1 plus c3, c1 x2 plus c2 y2 plus c3, all the way to c1 xn plus c2 yn plus c3. And that's going to be the same as z1 hat up to zn hat. Okay? And we know how to minimize this. So let's call this vector x star. We want to project b onto the column space of A. And we've seen how to solve this least squares problem. We want x star such that A transpose A times x star is equal to A transpose times B. So in this case, in this example, our matrix A is the matrix where the first column is consisting of the xi's, the second column consists of the yi's, and the last column is all 1, 1. 1, 1, 1, 1. And we got that because this C3 is being multiplied by 1. Okay, and we get that B is the matrix, it's the vector consisting of the zi's, and that's going to be 0, 1, negative 2, negative 1. And now we have to solve for x star. And it's, okay, if you solve for x star, it's better to use some sort of computer to do this, like a calculator or something. So it's C1, C2, C3, that's equal to negative 0.6, negative 0.6, 1.3. And so what that means is that the plane of best fit is z equals negative 0.6x minus 0.6y plus 1.3. I don't have a graph of these data points, but if you graph them, you'll probably see that it's a pretty good fit to the data points. All right, let's summarize what we did in this video. We found lines and planes of best fit, and we did that by showing that these problems of minimizing the sum of the squared errors, that amounts to a least squares problem, and we know how to solve the least squares problem, and we used that solution to find equations for the lines and the planes of best fit. And you can do the same thing for data points with n components, right? You're going to find the best n-1 dimensional space or hyperplane that will, the so-called hyperplane of best fit through those data points. Thanks for watching.